Stan Gibilisco here. I would like to talk a little bit about the evolution of an antenna known as a coaxial antenna. Now there are two ways to imagine the evolution of this type of antenna. The first way is to start with a ground plane antenna, a simple, basic ground plane with a quarter wavelength radiating element and four horizontal radials, each one a quarter of a wavelength long. You may have seen antennas like this on the Citizens band, which I also affectionately call the Chaos band, where an electrical quarter wavelength is about 9 feet or about 3 meters. So you'll see these elements horizontally and sometimes drooped a little bit. But if this entire assembly, the feed point right there where the coaxial cable joins the antenna, if that point is at least a quarter of a wavelength above the surface of the earth, and preferably more than that, then these four elements right there will serve as a very effective radio frequency ground. Even though they aren't connected physically, they don't need to be connected physically to the ground at all, they will serve as a very good RF ground, also known as a counterpoise. The impedance at the feed point, in theory, of an antenna like this is approximately 37 ohms, just as a vertical antenna would have over perfectly conducting ground if that vertical is a quarter of a wavelength tall. So that is where we start with the evolution of the so-called coaxial antenna. Now if you bend these radials down so that they're not horizontal anymore, but instead go down at an angle, when that angle is about 45 degrees for each of these four radial wires, the feed point impedance at the impedance at the feed point of an antenna like this will be a pure resistance equal to about 50 ohms, which forms a perfect match for most coaxial cables that ham radio operators will use. If you bend the radials down further and further and further yet until they're almost vertical, straight up and down, this radiation resistance will increase and will approach twice 37 ohms, actually 36.5 ohms, twice that value, or about 73 ohms. So for a moment, we'll journey into the far reaches of the solar system and clear our minds so that we can extend this little idea all the way to its extreme. Here's the feed point. Here's our quarter wavelength vertical radiating element, and we have four radials going straight down. And the coaxial cable passes right through the center of them and on down to the radio, preferably straight down from this whole assembly all the way to the radio. I just scrunched it here because I don't have any more room on the screen. But ideally you should run this straight down from the feed point for as great a distance as you can. Well, I don't think I've ever seen an antenna like that. But suppose that instead of those four radial wires, each one a quarter of a wavelength long, or maybe 3, or maybe 5, it doesn't have to be 4, suppose that we were to increase the number of these radials without limit until finally we had infinitely many of them in theory, so that what we in fact had, instead of 4 radial wires here, is a piece of metal tubing, like a conduit, a copper tubing, aluminum tubing, anything like that. This vertical element could be made out of aluminum tubing at many amateur radio frequencies till you get below about 40 meter frequencies. A longer wavelength than 40 meters, it becomes rather unwieldy. But suppose that you were operating this thing on 14 megahertz, 20 meters. That would mean that your vertical antenna element would be about 16 feet long, and also this conduit would be about 16 feet tall. You could guide this thing in the center with nylon ropes that don't conduct electricity or RF current, and have an antenna that altogether would measure 32 feet high, or a half a wavelength at 14 megahertz. This is known as a coaxial antenna, and it evolves from the ground plane by carrying the radial wire bending downwards to its extreme. The impedance at the feed point of an antenna like this is a pure resistance of about 73 ohms, which is a reasonably good match for 50 ohm coax. The same as the 37 ohms would be with a ground plane using horizontal radials. So you'd get about a 1.4 or 1.5 to 1 mismatch. Alternatively, you could use 75 ohm coax here, such as the television cable type coaxial cable. But as with all coax-fed antennas, your best bet is to get the lowest loss coaxial cable you can get your hands on. And that's usually RG8 or RG213U or its equivalents. The mismatch won't cause much of a problem as long as it's no greater than 2 to 1. You don't want a mismatch. Generally, it's best to avoid a mismatch with coax that's worse than 2 to 1, although you can get away with it, and I've done it in some instances and have made some videos about that subject as well. But that's one way that a coaxial antenna evolves. Now there's another way to think of an antenna like this. But before we do that, once again, we can journey to the far reaches of the solar system and clear our minds to refresh our minds for the theoretical discussion to come. Imagine instead that you take a dipole antenna, ordinary dipole antenna, made out of aluminum tubing. Each side is a quarter of a wavelength long, so the whole thing is a half a wavelength long. It's fed at the center, but this time you do something very interesting. Now these are the pieces of tubing. On 14 megahertz, they could each be 16 feet long, say an inch in diameter and 16 feet long. You could use a balun coil or balun transformer and feed that thing in the center and bring your coax straight away at a right angle from that dipole antenna for at least a quarter of a wavelength and preferably a half a wavelength or more to avoid antenna currents on the cable or minimize the risk of them. But there's another way to feed an antenna like this that is very interesting. Suppose that instead you run your coaxial cable through one of these pieces of tubing and you connect the shield of the cable to the side through which the coaxial cable runs, and you connect the center conductor of your coaxial cable to the other side. And then you simply turn that whole thing on its end so that instead of horizontal, it's now oriented vertically. Then you get yet another journey into the far reaches of the solar system. And, returning to Earth, magically you find that your antenna is now vertical, 16 feet. Remember again, this is a specific 14 megahertz coaxial antenna design. Your coax goes right up through this lower section. The shield connects to the lower section, the center conductor to the upper section. You have a very good base insulator here. Now this is an unbalanced antenna system in a sense. It's also balanced in another sense. So you could use a balun coil here. I'm not sure how much difference it would make. Now you might wonder about antenna currents induced on the coax from this lower section. Will that be a problem? And as long as you continue to run the coax straight down in line with this vertical for at least a quarter of a wavelength, and preferably a half a wavelength or more, that means you're going to have to get this feed point up there pretty high, a half a wavelength or more for sure. And of course, as I've said, you would ground it with nylon, or pardon me, guy it with nylon ropes. Run that cable straight down from that antenna for at least a quarter of a wavelength. I don't think you're going to see antenna currents on that coaxial cable, because inside of the tubing no radiation can take place. The radiation from this antenna goes out into space. It can't occur inside the conductor itself. So you should get no effects on here, and in fact get no antenna currents on your cable, as long as you obey that rule to run it straight away from the antenna. You don't want to run your cable out like that, because then you will get antenna currents induced like this, and that's a bad deal. So that is the evolution of the coaxial antenna as a modification of a vertical dipole. So you can think of a coaxial antenna as a metamorphosis of a ground plane or a metamorphosis of a vertical dipole. Those two designs converge in the venerable coaxial antenna, which I have used, by the way, on 20 meters with great success. Stan Gibilisco, proprietor and operator of amateur radio station W1GV, saying 73 for now, and so long.